Okay, we are back. And on this video, we will discuss about spherical coordinate system. We have already discussed discussed about Cartesian coordinate system. And something that we have to keep in mind is when we are referring to the Cartesian coordinate system, on this coordinate system, we do three transformations of translation. And we have a geometric solid which represent um, is where these transformations are done on the three-dimensional space. So this parallelepiped is which represent this coordinate system. And we can draw the axis. So right here we have the z-axis, the y-axis, and the x-axis, x, y, z, and is a three-dimensional space. And right here, the these transformations of translations can be done. And this is for the Cartesian coordinate system. And we also already has saw the cylindrical. Okay. And for the cylindrical, the geometric solid which represent is a cylinder within other one inside other cylinder. And is inside other one. Okay, and right here for the cylindrical, when we are referring to the cylindrical coordinate system, we have to keep in mind that we are referring two transformations of translation and one transformation of rotation. And we can draw its axis right here. We can have the z-axis, and is very obvious that on this z-axis we can do a transformation of translation. Um, but how can we do a transformation of rotation? This way? What do you think? Because this transformation, um, these transformations that we are doing on this cylindrical coordinate system, they are also three-dimensional. Right here is also three-dimensional, but this transformation of rotation, it needs to be referenced to the z or the y or x axis. Okay, so when we do a transformation of rotation on this coordinate system, um, right here is the x-axis, and as we are doing on the past videos, right here we are referring to this. Remember that we are doing a transformation of translation with about R. So I said that it was a device, a mechanism with the ability of it stretch itself, and it can reach to this point. So um, if let me draw the other axis crossing the system, crossing the geometric solid, and right here is y. How can we have a rotation transformation right here? Well, on this coordinate system, on both coordinate system, Cartesian, cylindrical, spherical, that we will discuss on this video, they come with a sequence of transformation. So, for example, if we have a first transformation of rotation, but let's do different. On the past examples from the past videos, we are doing a translation um, above axis, the x-axis, this way. And after this transformation of translation, we do a transformation of rotation. So it was on this point, the mechanism, and with the rotation, it goes to this point. But let's say we will do now a transformation, a first transformation of translation on the above the z-axis. So it goes to this point, and from here it can goes to this point. So in any axis that we will do a rotation, we need an angle, a alpha angle, and with this alpha angle, we will have cosine of alpha and sine of alpha, and this with like this we are referring to a x axis. So the rotation transformation is referenced to a axis. Okay, so it's a sequence of transformations, and for a translation transformation, uh, we are referencing the the transformation to only one axis, but for a transformation of rotation, we are referencing to two axes. Okay, and now let's start with the spherical coordinate system. So I will use the content of the third edition, and let me write what is being said on the book. For a spherical coordinate system, it consists of one linear motion, which is a translation, and two rotations. So on the same way that we were seeing on the past videos, it was passed to us a statement with a description of a, a motion, which is a sequence of transformations. So remember that it was passed and this sequence, uh, and on the same way for the example that we will solve, we have to use this statement as reference. So it says that the sequence is a translation of R along the z-axis, a rotation of beta rotation of beta about the y-axis, and a rotation of gamma about the z-axis. So again, we can draw this description. So this is a description of a motion that this robot, a arm robot is doing. So is a sequence of a translation of r along the z-axis, a rotation of beta about the y-axis, and a rotation of gamma about the z-axis. So we have to interpret this description and draw this description. In the book already provide that was, so I would just copy from the book. So we have to draw the XYZ coordinate system. X, Y, and Z. And we have a vector. And on the end of this vector, we have other reference frame. So this coordinate system uh, F, X, Y, Z is a reference frame, but at the same time a coordinate system. And on the end of this vector, which is a analogy to a robot arm and vice versa. So if is a analogy to a robot arm, we can say that on the end of this vector is localized the end effector, and on this end effector we have other reference system or reference frame, which is the FNOA. So right here, A, O, and N. N is a vector P. So now let's draw the transformations. It's a translation of R along the z-axis. So again, we have to take from this point, from the origin. So we are doing a, let me change the color for green. We are doing a transformation of translation along the z-axis R. So now we are on this point, and is a sequence. And the sequence is after the translation of R along the z-axis, it is doing a rotation of beta about the y-axis. So from here, we will do a rotation and is about the y-axis, but the y-axis is right here. Okay, so we have to, now as we are more experienced, we just need to please imagine that the y-axis is right here on this point. So from here we do a rotation, and it will help if I draw this is a rotation around the y-axis. And after this is another rotation transformation about or around the z-axis. Now it's up to you. How can we do a rotation around the z-axis as we are on this point? But first we had to project this point right here. Okay, from here, how can we do a rotation around the z-axis? How this going to look? Again, it helps if we draw this. So now we know we have a sense of direction that our rotation it needs to have. Um, is something like this. Okay. Okay. So we do a first transformation of R to this point, which is alongside the z-axis. And when we were on this point, the second transformation that from the sequence, it was a rotation of beta about the y-axis or around the y-axis, and it helps if we do this. So we know we have a sense of the direction that this arrow it needs to be pointing. So is on this direction, and after this we have to project, and I use this dashed line. So right now we are on this point because it's pointing towards to this x-axis. And right now, and the last and third transformation is another transformation of rotation of gamma um, about or around the z-axis, and it helps if we draw this arrow, so we have a sense of in which direction the arrow it needs to be pointing. So it is something like that. And I will have to correct this because it's more easy if we actually project these points on the axis. Uh, we need to use the end of the vector or the end effector of the robot as reference. So this is going to help right now. We will project from this point to the end effector of the arm of the robot or from the vector and project right here. I will need to do this smaller, and projecting to the end effector of the robot arm, and this is beta angle and this is gamma angle. And again, from the book, it says that since these transformations are relative to the universe frame, and just by mention universe, you might think so. Oh, is U frame, okay? But if you remember, we can say that this universe frame, instead of use the letter U, we will use the letter R, and is just the nomenclature Um, we can say that this R is from robot or from reference frame. And we will not use the letter U to write the transformation. The total transformation can be found by pre-multiplying by each matrix. So it's different from the examples in which some transformations are defined and passed to us as coordinates. Right here, we are able to construct this matrix since we are able to interpret the text. So this is a very nice example, a very nice exercise. It is a good exercise. Right here, we are doing a text interpretation, and with this text interpretation, we can do this draw. Um, so is a text. We are doing a text interpretation of a text description. So look how nice it is. This description is a description of a motion of a robot, and with this description of this motion or task that this robot is doing, we can draw another description, which is the description a more visually description. So we do a interpretation of a task description, and with this we do a draw of this description. So it's a draw description, and within of these descriptions of the task um, of the text, which is a task, or of the draw, we can write the transformation equation. And again, the transformation equation is another description of what this robot is doing. So let's use this, both the task description and the draw description. It will lead us to the transformation equation. So right here is R. In the book, it don't like clears if it's from robot or reference frame. But if I'm not wrong, maybe probably I have read that this reference frame, this R is from reference frame. It's just a nomenclature. So the total transformation is again what this end effector is going to be at the end of the task. So the total transformation is a transformation in relation of the P frame, is a transformation of the P frame in relation to the R frame. So right here we have just write our first transformation. Okay, and the second transformation, and again, this reference frame, it turns is a coordinate system, but right here on this origin, um, this reference frame, it turns into a reference to this other reference frame. Both are coordinate system, but at the same time a reference frame. So R is a reference. Sorry. No, exactly. R is a reference to P, but we write and we read P referenced to R. So P referenced to R. And now a translation of R along the z-axis, and is a translation of R along the z-axis. And just like we were seeing on the past videos, from R axis, as this first transformation is above or alongside this z-axis, we have 0, 0, and R, because this is the order is x, y, and z. Is a linear transformation. It goes only on the z direction, and we don't have any component on the y and on the x axis. So this translation we can write this way: 0, 0, R. And let me place this a little bit up about right here. Okay. And the other transformation is a rotation of beta about the y-axis. So for rot, a rotation on the y-axis with some beta angle. And the last one is another rotation of gamma about the z-axis. So it's a rotation on the z-axis with some angle gamma. And again, we have to pay attention on the notation. This is a transformation on the spherical coordinate system. R, beta, and gamma. Okay. And let me bring this other transformations. Okay, so we have just write our transformation equation. And now let's copy the characteristical transformations of rotation, characteristical transformation of rotation above the axis. Let me find right here the characteristical transformations of rotation above the axis. Let me copy and we will use it. So above or around the z-axis, okay, and we have to add the scale factor to keep this matrix on its quadratic form. And right here is gamma. And remember that the order in which we multiply the matrices influence on the final result, and we have to do the on the correct order. And something that I got confused is on the book the description of the sequence. It diverges on the sequence in which these transformations are being multiplied. Okay, so is gamma. And now adding the scale factor. Right here is one. Okay, and now the characteristical rotation matrix above the y-axis, this one. And these angles, they are beta, and adding the scale factor. Beta, and the scale factor. Okay. And now the characteristical matrix of a translation is a matrix with its main diagonal filled out with ones, and the rest of the elements are zero. So it's 1, 0, 0, 0. And right here for Z, we have our Okay. And now we have to multiply these matrices, and we will obtain the total transformation that are the final orientation and position, which resumes on the localization of the end effector or the point of the vector, doing an analogy to vector. Okay, so a robot arm, we do a analogy to a vector, and we are doing this is the most simple example. um, I think this video is too long, so I will perform this operation in another video, and this is going to give to me more time to explain this draw to you better, and we can finish this video using the octave. And so let's open the octave. Okay, I'm already got the octave open, and let's write these matrices and do this operation. Okay, so let me use this. Let me copy this and use very quick. So let's call the first matrix of A. So this is cosine of gamma, sine of gamma, zero zero, sine of gamma, cosine of gamma, 0 0 0 0 1 0 0. Okay, but we have to type a command so the octave can recognize these parameters. So we have to type, let me just copy this. So okay, so we will load this symbolic package, and we have to type this command. So octave will recognize these parameters. So they are gamma, beta, and R. Okay. Perfect. Now let's bring our matrix. And the first one is that one. Let's just copy. Nice. So the other matrix, now let's call of B matrix. n is equal cosine of beta. Right here is 0. And sine of beta 0. Right here is 0. One, 0 and 0. Right here is minus sine of beta. 0 cosine of beta. 0, 0, 0, 0, 1. Okay. Perfect. And now the last one, the translation one. So let's call off C matrix and let's use this one, which don't contains any cosine and sine. Exactly at that one. So is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right here is R. 0, 0, 0. Oh, okay, exactly. So let's copy and paste on Octave. Nice. Now let's multiply them. And let me compare with the book and see if we are correct. So first, let me pass the result, the final result, and again paying attention on the notation, which is very important. Is a transformation on the spherical coordinate system. R beta and gamma, and the total transformation, it has these elements, these values or components, whatever you want. Okay, and now I'm going to take a screenshot, take a print from the Octave screen and compare with this. Okay, let me bring to here. And let's compare each element. This one is first is correct. This one is correct. This one is correct. Correct. Is correct. Correct. Is correct. Okay, that's perfect. They are correct. They are all correct. And when I was doing this operation with these matrices on the past videos, I was committing a mistake, and but now on the next video I will do the same example with you and try to explain better this draw that we did on this video. Um, and also I will perform this operation between these matrices, this multiplication between these matrices, and correct me something that I did wrong, and add something that I forgot to say to you. And that's nice. We are we are getting there, getting somewhere. And after this video, we will solve another example. So we have the example from the third edition, the example 2.12, and from the second edition is the 2.19. And after these examples, um, we got articulated coordinates. And after our articulated coordinates, we got equations from kinematics, forward and inverse kinematics, and in which we will discuss about topics of angles, and we will get into something new and also very nice. It's just a bit complex, but if you follow to hear all these videos, so you have a base to keep following with the series. And for now, I think it's all. So thank you.